All right. Hello again, everyone. Welcome to the last session of today. Again, I'm David Adam from the NNSA Advanced Simulation and Computing Program, and we have two presenters here to round up the afternoon. First up, we have Nishad Maskara from Harvard University. His field is physics, and he did his practicum at Lawrence Berkeley National Laboratory in 2022. And today, his presentation is on towards useful quantum simulation with reconfigurable Rydberg atom arrays. So let's welcome Nishad.
Hey everyone, thanks for the introduction. So I'm very excited to tell you guys today about some of my PhD work. So I work in the Lucan group at Harvard, and broadly speaking, our group is working on building quantum computers. So in particular, the types of things that I'm most excited about in the field of quantum computing is using it for simulating quantum antibody systems. So a few years ago, a lot of the efforts in our group centered around using our devices in kind of analog fashion to realize exotic phases like topological spin liquids, and also to study dynamics of strongly correlated quantum systems. However, the long-term vision of quantum computing for simulation is to really try and target, interesting real-world molecules and materials, real-world quantum systems, in order to make predictions about nature. And really the potential of quantum computing to accelerate a lot of computational science is really quite exciting because, as many of you guys know, simulating the quantum effects that occur in nature is actually a very challenging problem. Now, I'm not the only person excited about this. Many people are. And recently, the Microsoft group ran some pretty detailed estimates for how expensive would it be to run a quantum simulation on potential futuristic hardware. And actually, if you look at some of these numbers, they're kind of discouraging. So here, for example, they studied how expensive it would be to compute the ground state of some ruthenium catalyst. And what they find is that, even on futuristic hardware, it would potentially take months of time to actually do this ground state energy calculation. So, that's still extremely expensive and probably beyond the realm of practical usefulness. So what we've really been doing is trying to understand, where are these costs coming from and how can we potentially address them? And, really it breaks into three things. Like the encoding of the problem is expensive, the algorithm they're using to solve the problem is expensive, and also quantum error correction, which is necessary for getting high accuracy, is also super expensive. And so in our group, what we're really working on is co-designing the architecture, the hardware, along with all three of these things, the application, the algorithm, and the error correction, in order to really try and reduce these resources to make them much more realistic. So my talk is going to be kind of a broad survey of some of the things that we've been exploring. So let me jump right into it. So first, I'll give kind of an overview of the platform that we have in our lab. So the platform is known as the Reconfigurable Atom Array architecture. And it has essentially what we do is we store our qubits in two hyperfine states of an atom. And by exciting the atom to a highly excited Rydberg state, we use that to generate interactions. And some of the really unique opportunities in our platform is the ability to engineer very efficiently non-local connectivity, and also the ability to very efficiently control the system in parallel. So how do we actually realize interactions in the system? So when the atom is in the qubit state, the ground state, the electron is very closely held to the nucleus. However, by exciting it to this highly excited Rydberg state, the atom becomes much bigger. And as a result, if we bring two atoms really close together, they interact with very strong van der Waals interactions. And in fact, we can make this van der Waals interaction so strong that two atoms that are next to each other can't be excited simultaneously. And the fact that two atoms can't be simultaneously excited is a source of nonlinearity that we can use to really generate our programmable interactions. So this nonlinearity was really used in some of these analog experiments that I mentioned in order to generate strongly interacting phases of quantum matter. And in these settings, what we really do is we kind of position our atoms in arbitrary places, and then just by exciting to the Rydberg state, kind of study the dynamics of this underlying system. However, recently, we've been really exploring how we can use this system in a more digital mode, where we start to really run quantum circuits using these devices. And this really opens up a whole new slew of opportunities because once we can do discrete operations, we can really realize a universal quantum computer. Now, how do we actually use this device in digital mode? So the key is that, one of the two keys is that the positions of the atom determines the connectivity of the underlying system. So in order to implement gates, we would take our array and group the atoms into small clusters, maybe say with 2 or 3 atoms per cluster. And then we would pulse the system globally. And by using some essentially pulse design, pulse engineering techniques, we can efficiently engineer target interactions within just say the adjacent 2 or 3 qubit clusters. Now the second key ingredient is the ability to actually move atoms in parallel. And in fact, just by moving the optical tweezers at some slow speed, you can kind of move the atoms while preserving coherence. And by combining these two things, we really have now an architecture for doing some programmable quantum computation. So for example, here you can see an example of a circuit that was run in the lab where the atoms are kind of being moved and pulsed in alternating fashion in order to realize some complex circuit. And we'll kind of get back to the circuit later in the talk. Cool, so that's kind of like a very high-level overview of the platform. Next, I'll talk about some ideas we've been developing for how to efficiently encode interactions, complex Hamiltonians, into this type of device. As an example, I'm going to use the Kitaev honeycomb model, which is kind of a canonical example of a very difficult model in condensed matter theory. And so far, this model has primarily lived in theory because it's really hard to engineer. It has very anisotropic interactions associated with like an XX, YY, and ZZ term that all act on 3 different types of links. Furthermore, this model has a really interesting phase diagram. It has abelian topological phases and non-abelian topological phases. And if you don't know what those mean, you don't need to know. The important thing is just that it's a very challenging model with lots of interesting physics. So this anisotropy is really like a key challenge that was difficult to overcome for a while. Now, by using this kind of parallel architecture with reconfiguration and gates, we can actually efficiently realize this type of system in a digital way. So the kind of key idea is to split the interaction up into 3 parts. During the first step, you move the atoms around and then apply a laser pulse. And this time, the laser pulse is oriented so that it applies interactions along the x direction. Then you again move the atoms again, change the connectivity of the lattice, and then again apply another global laser pulse. This time, it's oriented along the y direction. And then we again move the atoms one more time, and then apply another laser pulse. And in the third step, this time it'll be oriented along the z direction. And by kind of just alternating these 3 sequences, one after another, we can very efficiently access this entire phase diagram. Now, some of you may be wondering, well, okay, you took this Hamiltonian and split it up into discrete steps. Doesn't discretization introduce some errors? Well, it turns out that in this particular model, these higher order errors that get introduced are actually a good thing. These errors actually help us to stabilize the phase that we're trying to engineer. In particular, this non-abelian phase, these errors actually increase the gap, which makes it more stable to unwanted perturbations in the system. Okay, so this honeycomb model is, I think, a very nice example for how you can use this reconfiguration and pulsing to realize a complex model. And since then, we actually spent some time thinking about how to generalize this to really complicated models. So in particular, we studied generic spin models, not just this particular one, but generic spin models. And actually, so during my practicum, I visited the Head-Gordon group at Berkeley. And what we learned is that by being able to engineer complex spin models, we can potentially study different types of strongly correlated magnetic phenomena that are also present in different types of molecules and materials. In particular, when you have localized valence electrons and charge fluctuations aren't important. So these spin models can oftentimes be derived or computed efficiently using certain ab initio approximations. However, they're kind of a really canonical example of a strongly correlated problem that's really difficult to solve classically. Most of the state-of-the-art methods really come with exponential overhead. So they're kind of really a nice intermediate because they have a very natural mapping onto our quantum hardware. Okay, so that's kind of a high-level overview of some ideas related to engineering the Hamiltonians using these devices. Next, I'll talk about some also new ideas related to developing algorithms. So just being able to simulate the Hamiltonian isn't enough to really solve a molecular material problem. Instead, it's really important to actually ask, well, how do we extract information that's useful? So the traditional quantum computing approach is based on computing the ground state energy of a molecule using something like the quantum phase estimation algorithm. So the phase estimation algorithm circuit looks something like this. And the really important things to note is that it's very expensive because it includes these controlled unitary evolutions. And as such, it's also really sensitive to noise. So in order to make this algorithm work, you really need a very, very low error rate, fully fault-tolerant quantum computer. And as such, it's kind of hard for us to access in the near term. However, we already have these quantum simulators in the lab, and they're really, their capabilities are increasing every day. And so we kind of asked, well, what does the system that we already have naturally do? And what it really efficiently does is it simulates time evolution, but it also gives us access to projective measurements of individual qubits. So we call these things snapshot measurements because they're essentially pictures of the system. And we were kind of wondering, well, what can we do in combination with these dynamics and these pictures? So this is also something that I worked on during my practicum. And what we realized is that we can actually use this information to compute everything that quantum phase estimation gives you, all of these energies, and also a lot more detailed information on top of that. So the way we do this is by efficiently computing what we're calling an operator resolved density of states. This thing has two parameters, an operator A and a frequency omega, which gives us access to eigenstate properties and the eigenstate energy, respectively. And the algorithm is actually a hybrid algorithm that uses a lot of classical processing in order to take these snapshots and turn it into this useful information. And it's based on this complicated-looking expression that really breaks into three parts. The first is the sum over observables, which comes from the snapshots. The second is this correlation function evaluated at 0 time, so that has a very efficient classical representation. And the third is based on these quantum time dynamics. And this is also the part that's hard to simulate classically. So really, in this approach, we've isolated what the quantum computation is doing. It's just simulating time dynamics of correlation functions. And from that, we're actually directly getting some interesting molecular type properties. And here's just an example of the circuit. So let's kind of illustrate what this would look like if we were studying a spin model associated with this molecule. So the spin model has some low energy spin spectra. And if you zoom into it, you see a bunch of really closely spaced peaks. But by also using this operator resolution, we can also do something like measure the total spin of each of these low energy peaks, which allows us to compute something that's often known as a spin ladder. And the spin ladder is something that can also be measured experimentally. So let's say you have two proposed structures. You can compute the model Hamiltonians of these two proposed structures and compute the low energy spin ladder associated with each of them, and ultimately compare those to experimental measurements to determine which structure is more likely. All right, and with that, I'm almost out of time. But I would also like to mention some kind of new developments that we've been pursuing in terms of very efficient approaches to error correction using this device. So really the key challenge to scaling up quantum computers and to solving really challenging, really important problems is fighting decoherence. And in particular, we want to be able to realize really low error rates, things that are like 10 to the minus 10. But all the known ideas for how to do it in hardware only give us things like 10 to the minus 3 or even 10 to the minus 4 optimistically. So, in order to solve this, you need to encode your qubits in error-correcting codes, which is too much for me to talk about today. But, really the takeaway is that you can, once you've encoded your qubits into error-correcting codes, using really the same tools that I discussed in the context of the Hamiltonian engineering, you can also very efficiently do operations on the error-correcting codes themselves. So, for example, you can do single logical qubit operations by pulsing an entire error-correcting block at a time. And then by moving error-correcting codes around in the system, you can also very efficiently realize interactions between these error-correcting codes. And these operations are really nice because they also actually have good properties related to error propagation. And because we're moving around the blocks kind of globally, we can also realize long-range connectivity between the code blocks themselves. So these, even though we're doing this overhead associated with error correction, actually at the level of the control, it really kind of preserves a lot of this simple parallel control from before. So, okay, what would an error-corrected simulation look like? So you start by encoding your information in an error-correcting code, and then you run some circuit. This circuit now acts at the logical level. But then at the end, when you make your measurement, the measurement kind of splits into two parts. You can extract from it the logical information, which is what you're trying to simulate, but then you also get this extra stabilizer information. The stabilizer information contains the redundant information that lets you know whether or not you had errors occur in the system. And by looking at the stabilizer information, you can get some confidence about whether or not an error occurred during that phase of your computation. So, we can kind of ask now, so there's a lot of overhead associated with doing this encoding, but are there interesting questions that live in the realm of easy to implement error correcting codes in the near term? And actually a very interesting code is this 832 code, which is 8 physical qubits and 3 logical qubits. And it also has a really powerful native gate set. And this native gate set contains a CCZ interaction, which is classically very challenging to simulate. So we were able to run experiments using 128 physical qubits that encode 48 logical qubits in order to really simulate the distribution associated with this 832 codes. And here, for example, is a picture that shows how the distribution that we sample from improves as we increase how much of the stabilizer information we're utilizing. Okay, and with that, I hopefully have kind of illustrated this idea of how we can, by combining hardware, algorithms, applications, and error correction, really try and advance, usefulness of early kind of fault-tolerant quantum simulations. And with that, I'd like to thank all of my collaborators and also the experimental team. And thank you all for your attention.